we start, welcome everybody to the WISDOM YoungWomen4OR webinar, latest advances in mathematical optimization. Before I start, I would like to remind you that this session is being recorded so that we can upload the recording to our YouTube channel. And I would also like to remind you that you will have the chance of unmuting and sharing your camera at the end to ask questions to our three YoungWomen4OR awardees, but also to take a nice picture about the event. So let me go to the next slide. So as you may know, WISDOM is one of the Euro forums. So we like to provide a platform to support, empower, and encourage the participation of all genders in operational research within Euro. And we have mainly three goals. So advise, make recommendations, highlight best practices to the Euro executive on issues women face in OR. We also like, such as the event of today, to promote championing, networking, and mentoring, particularly of women at the early stage. And you know that today we have three of the YoungWomen4OR awardees. And finally, we promote a conversation around how OR can be utilized to help create a diverse and inclusive future. So we have had already 4 calls for YoungWomen4OR, and actually we have currently 1 open. We will talk about that later on. And this is the last webinar of 2024. So we are counting today with Emilia from Karlsruhe University, Kübra Tanınmış from Koç University in Turkey, and then Mariana da Cunha from Portugal. In addition to these YoungWomen4OR awardees, we also count with the presence of Professor Andrea Lodi, who is a full professor at the Jacobs Technion Cornell Institute at Cornell Tech and the Technion. So he is a very well-known colleague in the area of mixed integer, linear and nonlinear programming and data science, and that's the reason why today he is our expert in this session. He has not only worked at Cornell, but he has been at the University of Bologna, full professor. He has also had Canada Excellent Research Chair in the Polytechnique Montreal University, and he has also worked for IBM in various positions. So Andrea has been a principal investigator of scientific projects involving industrial partners for Italy, the European Union, Canada, and the USA. And yes, he has also given many plenary keynotes at key conferences. We are very, very happy that he took the time today to join us. So I would say that this is a very brief presentation of the 3 YoungWomen4OR awardees and of our subject experts. So I'm keeping it short because I would like to make sure that each of them got the time to speak. So I'm going to stop sharing my slides, and then we will have Kübra giving our first presentation. And for the audience, please know that after Andrea has given some insights on the papers, we will open also the floor for questions. Kübra, the floor is yours, and I apologize if I didn't pronounce your name very well. So Kübra will be talking about Benders decomposition, so we are very happy to have your talk today here.
Thank you very much, Dolores. No, it was fine. It was super good. Kübra is my name. I'm Kübra Tanınmış from Koç University, Istanbul, and I will present you Benders decomposition algorithms for the minimization of spread of harmful contagions. This is the outline of my talk, And I will first introduce our problem, measure-based spread minimization problem. Then I will present two integer programming formulations and their vendors decompositions, mention some implementation details, and share some summary results, let's say. Okay. When we talk about harmful contagions, we usually talk about the spread of undesired things such as rumors, misinformation, or fake news, or sometimes diseases. And we want to stop them or at least limit them. And one approach to do so is to start an anti-campaign, and then it's called influence blocking maximization. Another approach is to block some network components such as individual nodes or edges, or blocking edges or nodes as groups. And this is the part that we focus in this work, and it has not taken much attention so far. And in this direction, in similar direction, there are some heuristic methods. Most of them consider a simplified measure of the spreads instead of the expected spread itself. And there are no exact methods for the minimization of spread. In this problem, measure-based spread minimization problem, we are given a network. We are given that a harmful contagion has started at some seed set I and spreads with some stochastic diffusion model M. We want to limit the spread via edge blockings. And we are given some measures, denoted by capital K, let's say. And we can take some of these measures. And when we take a measure, let's say K, the arcs that are associated with this measure, they are removed from the network. So our arcs have labels associated with the measures. Some examples to such actions are the COVID-19 measures, such as closing of schools. When we close the schools, we prevent the connection among students. So we do not individually remove some connections from the network, but as a group. And we are given a limited budget for taking measures. We denote the expected spread by sigma, and the measure-based spread minimization problem involves finding a subset of available measures within the budget, such that in the remaining network, the spread is minimized. There are two very common diffusion models, independent cascade and linear threshold models. These are stochastic and progressive diffusion models, which means that once a node becomes infected or active, it cannot go back. And these models can both be represented by live arc scenarios. And a live arc scenario is simply a subgraph of the original graph when some of the arcs labeled as live with some probability distribution. And this distribution determines the exact diffusion model. And under this diffusion model, our objective function is neither submodular or supermodular, which means that if we develop a greedy algorithm, we will not have an approximation bound. This is an example. We are given the arc labels on the arcs, and we are given the seed set 1 and 4. These are our initially infected nodes. This is one scenario. We have a subset of the arcs. These are the live arcs of this scenario. And we decide to block label 2, or take measure 2, in other words. This is why we see dashed lines here. And since 3 and 5 can be reached via live arcs, they get infected in this scenario. In some other scenario, there are different live arcs, and 3 and 4 get infected. And here we see yet another scenario. And we propose two integer programming formulations. The first one is an arc-based formulation. We assume that we are given a set of scenarios denoted by omega, which means that we are given the live arcs of each scenario. Our decision variables are xk, which is equal to 1 if label k is blocked or measure k is taken, and yi omega, which is equal to 1 if node I gets infected in scenario omega. So the objective function is the minimization of average spread, average number of infected nodes. We have the budget constraint, and we have the constraint that any seed node is infected in every scenario, and the arc-based spread constraint. This one tells us that if we are given a live arc ij and node I is infected, if we don't block the label of that arc, label k, then node j also becomes infected. And we have our variables are binary variables. We apply a Bender's decomposition method. So x variables goes to the master problem, rest goes to the sub-problem, and we define our dual variable. I will skip the details of this part. This is our Bender's optimality cut. And we don't want to solve the dual sub-problems as LPs. Instead, we make some definitions and propose a combinatorial procedure. We consider the graph, which is weighted by the blocking solution, the upper level solution, x bar. So if an arc has a label k, then the length of arc is x bar k. And we calculate the shortest path distances from the seed set. If the distance of a node is strictly less than 1, then it is a reachable node. Otherwise, it's not reachable. And the path associated with this shortest path distance for a reachable node is called an activation path. Okay, these are our definitions, and our theorem tells that if we choose alpha beta such that alpha I is the number of activation paths starting at I, beta A is the number of activation paths passing through arc A, then this is an optimal solution. We don't need to solve an LP. And the second one is a path-based formulation. The difference is in the spread constraints. For this part, we assume that we can enumerate all the paths from the seed set to every other node. And for a given node, I, and paths from the seed set, if the number of blocked arcs on this path is equal to 1, then the right-hand side becomes 0. If the number of blocked arcs is 0, the right-hand side becomes 1, and our node I becomes infected. This is not a compact formulation because we need to enumerate all the paths, and we show that this have the same LP relaxation bound as the previous formulation. The Bender's master problem for this formulation is the same. For the dual subproblem, again, we have one subproblem for each scenario. The nice thing about the dual subproblem is that it's decomposable. One problem for each node. And for each node I, we need to find the path P such that this summation is minimized. And this is exactly the length of the path P. So we need to find the path with the shortest length. And this is what our next theorem says. If we choose gamma, our dual variables, such that gamma IP is equal to 1, if P is the activation path of node I, then it is an optimal dual solution. This is the resulting cut. The constant part is equal to the number of reachable nodes in that scenario, and the coefficient of variable xk is the number of arcs with label k on all activation paths. Okay, next we lift our cut. We simply draw the frequency of our labels and just count the number of blocked labels on the paths. The dual subproblem is still decomposable, but the previous theorem does not hold because this summation we see here is not equal to the length of the path. Yep, we implement a branch and Bender's cut algorithm. We separate both integer solutions and in some of our settings fractional solutions, and we propose two heuristics for the lifted optimality cuts. We have some additional components like having unblockable labels and sampling ratio of cuts, because we don't have to generate one cut for each scenario, and we have initial solutions. And now I will quickly present you some results. This is a summary of our instances. We have both real instances and random ones, Barabasi Albert and Erdős Renyi. And these are our parameter values. And in our algorithmic settings, we just add our components one by one, in sequence. So we add fractional separation, cut sampling, and lifting. And these are the cumulative runtimes. We see that as we add more algorithmic components, we can improve the solution times. We can solve more instances in the given time limit of 1 hour. And here we see that if we check the last column, if we solve those problems as LPs, we can solve only one out of more than 500 instances, while our combinatorial procedure improves the number of optimally solved instances dramatically. And some possible research directions are considering node blocking, partial blocking of network components, and considering fairness. Thank you for listening.
Thank you so much, Kübra, for making this presentation truly on time. We will take the questions at the end. So now we will switch to the next presentation by Emilia.
Yeah, hi. I start to share my screen.
Yes, please.
Can you tell me if you can see it?
We can see it. Thank you so much.
Perfect.
So the floor is yours, Emilia.
Thank you so much for having me. My name is Emilia. I'm a junior professor at the Karlsruhe Institute of Technology currently, and this project, the machine learning approach to deal with ambiguity in humanitarian decision-making, was a joint project with János Ortmann and Walter Reif from the Kübra University in Canada and Borje Balcik from the Özgün University in Turkey. And let's start with why are we dealing with ambiguity and ambiguous information in humanitarian operations? After disasters, it doesn't matter what kind of disaster, earthquake, civil wars, and so on, the situation is pretty chaotic. No one knows exactly how many people are affected, to what extent, what they need. This is why relief agents try to collect as much information as possible, for instance, by interviewing local experts, community leaders, key experts, affected people, and so on. The problem is that these data sources provide often very divergent estimations. So if you ask 3 experts, you get 3 absolute different need estimations. And these differences and inconsistencies lead to ambiguity the relief agency has to deal with. And what is often done in practice is to combine all these different values into a single value by simply applying some kind of aggregation technique, taking the highest value or just the average, and based on the single value, we do the decisions then. The problem is when the data that comes from different sources and is aggregated into one single value, it's not possible to say what effects aggregation will have and at the end on the final decisions. And therefore, we present a new method that integrates all this available data, the needs assessment into the decision-making directly, taking ambiguity and uncertainty into account. And while our methodology is in principle general, it can also be applied to different decision-making settings. Here we are focusing on locating shelters in the aftermath of disasters, where it's very difficult to obtain accurate information. And our network consists of nodes, these districts where shelter demand can arise, where we try to open a facility such as tent that could be set up to meet this demand. And our optimization model is then formulated as a 2-stage stochastic model, where we have 2 types of decisions. In the first stage, that means before demand is realized, we have to decide where to open and locate shelters. And when the actual number of people requiring shelters is known, so demand has realized, then second stage decisions are taken on how many people can be accommodated, and these are then the second stage decisions. And our objective is to maximize the expected number of accommodated people, and as usual, a set of scenarios is used to incorporate uncertainties, where each scenario contains the estimation, for instance, of shelter demand. Okay, and these scenarios will then be essential for our methodology. Sorry. Basically, we propose a two-phase framework consisting of the descriptive and prescriptive phase, and the objective of the descriptive phase is to analyze the information provided by different data sources, and also to evaluate to what extent do they agree, for instance, on shelter location. The key idea is that they might provide different estimates, but they would still agree on the shelter locations on the decisions at the end. And we can then use this knowledge to find an optimal solution by integrating all the data in our optimization model to reach then a consensus decision, okay, in the prescriptive phase. We want to find shelter locations that all these experts would agree on. Okay. First, the scenario generation. So after collecting data from different data sources, data has to be translated into scenarios for each data source K with corresponding probability distribution P. And based on these scenarios, we compute the so-called opportunity cost distance, because the question is, how much does it cost if we prepare for one scenario, but another would realize? Okay, so low costs mean that two scenarios are very close, meaning that the shelter decisions are very similar. So even if different data sources would estimate shelter demand differently, they might still agree on the shelter location, on the final decisions at the end. And this is exactly what we've done in the clustering step. We are looking for groups of scenarios that are very close to each other and far away to the others, and close to each other mean where the shelter locations are very similar. Okay, and for this we used an unsupervised machine learning algorithm. And based on this, we can then analyze the level of ambiguity. So first, we check the decision level of agreement, which measures to what extent different sources agree on the same shelter solutions. Meaning a delta of 0 is a complete agreement, so we have identical solutions, while a delta of 1 means total disagreement, so no overlap in locations at all. And then secondly, we consider the distribution of data sources within a cluster, because we are interested in clusters with as many data sources as possible. The more data sources are present in one cluster, the less ambiguity is involved between them. Because, again, different data sources might provide different assessments, but they still lead to similar or even equal and same location decisions. Okay, and we use entropy to measure this diversity. And again, a value close to 0 indicates a very low diversity, all scenarios coming from the same data source, while a large value indicates high diversity of data sources. Okay, and then these insights are then used to choose the weights W so that we achieve a consensus decision X star. If different sources with different estimates agree on the same shelter solutions, we place more weights to the corresponding scenarios. And we also place more weight on scenarios generated by data sources that appear in more clusters. Okay, because then we see that the ambiguity level is lower. Okay, so this is the general approach, and we implemented this framework to the problem of locating shelters for internally displaced people in Idlib due to the civil war in Syria. An Idlib district consists of 26 sub-districts, and we can choose not more than 10 shelter locations within the Idlib region. Each of those 80,000 of people that can be accommodated. This are real data taken from 2018. Okay, and we focus on two data. sources that is provided by the, first of all, the humanitarian initiatives, HNO, this is source 1, and READ, which is source 2. Yeah. And in the first step, we randomly generated 1,000 scenarios, so 500 scenarios for each source, and each scenario can occur with the same probability for this particular case because we assume that each source is equally reliable. Okay, but we can differentiate here. And we can see here that the distributions of these scenarios can significantly differ. For instance, for YW4OR, the estimates for the shelter needs differ significantly. Okay, we don't have any kind of overlap, whereas in Harim, the demand estimations almost completely coincide. Okay, so obviously we have a high degree of ambiguity for some districts because they don't even overlap. The question is where to open shelters in such cases of disagreement. Yeah. Due to our clustering approach, we generated 9 clusters, where source 1 split over 8 clusters, the blue bar here, and 1 orange cluster consists only of source 2. And we see 2 things here. First of all, source 1 predicts a much higher level of uncertainty than source 2, as it is present in more clusters. And on the other hand, the clusters are very homogeneous. In all clusters, only one data source is present. So there's no diversity, no entropy. And so we can see here, on one hand, both sources disagree with each other. And on the other hand, at least for source 1, there's relatively little consensus on shelter locations within the clusters. Okay, so we have here a high level of ambiguity. And we used these insights to define the right weights, W, for optimization model to produce consensus decisions and then compare those with other approaches. In particular, we compared them with an expected value approach, which is very quite often used by humanitarian agencies. So we use simply one mean value of the shelter estimates as the representative scenario. Then the second one is the traditional stochastic program, where all scenarios are equally treated. And then the third approach is our clustering approach, where we use the insights from the ambiguity analysis to set the right weights in an appropriate way. And the question was, which approach is best with respect to demand satisfaction? Okay, so we can accommodate. So where can we accommodate most people? And for this purpose, we carried out of sample tests where we generated 10,000 scenarios just randomly, and we used different shelter solutions provided by these 3 approaches. With these shelters, how many people can be accommodated? That was the question. And we can see here in this table the gaps that are given between the objective values of these 3 approaches compared to source 1 and source 2. For instance, if we use the expected value approach, that would lead to a solution where almost 23,000 fewer people can be accommodated than in the solution based on source 2. So if expert 2 had been right, then almost 23,000 people couldn't be accommodated. On the other hand, the stochastic approach gives much better results with a smaller gap for source 2, but at the expense of a higher gap for source 1, which is pretty low, but still significant if you scale it up. Okay, and if we look at our clustering approach, it provides the lowest results, meaning that our solution best integrates the information coming from both sources. And the advantages of
so
this
1 minute, please.
Yeah, you're absolutely right. So just briefly, the framework is applicable to general optimization models and deal with ambiguity and uncertainty. And we also could show that additional tests is particularly valuable if the expected value, if our approach is beneficial for a wide range of source estimate, less consensus on the solution, and a wide diversity of sources within the clusters. And with this, I would like to thank you for your attention. Thank you, and sorry.
Thank you so much for such a nice presentation, Emilia, also as the one before. So we now move to Mariana. Could you please share your file? Yeah, that's fantastic. Yeah, that's fantastic. So the floor is yours, Mariana.
Thank you. So I'm Mariana, I'm from Lisbon, and I'll be presenting a framework for computational efficiency and user interaction in multi-objective optimization. So when we have a multi-objective problem, we don't find a single solution. We find a Pareto front comprising a set of non-dominated points. And here on the bottom right, you have an example of such a Pareto front. And as you can see, even for this is actually an illustrative example, so it's a small problem, the Pareto front is quite large. And so when faced with so many alternatives, it is difficult for a decision maker to choose upon a solution and make a decision. It is also often very difficult to compute so many solutions, and it's time consuming on both ends. So just for motivation example for our problem, well, imagine a person would like to buy an apartment, and they want it, or usually want it, to be as large as possible, as cheap as possible, and very close to a city center or to a specific location. And that's often difficult to satisfy, or a lot of times impossible to satisfy to the maximum each of these objectives. And so if they search online, they will find that this is Lisbon, and you will find many solutions. So what we would like to propose is that when you look, for instance, when you look online, instead of seeing so many solutions, the website can select a set of solutions to show to the decision maker, comprising a house portfolio, and then a refinement of the list can be made, providing on the interactions with the decision maker. So what we propose is a combination of three models. So first, a representation method, where you take, for instance, here our original small example, and you do, there is a representation of the original problem. This representation should be as small as possible, be as well spread as possible through the Pareto front, but that captures the traits of the Pareto front. Furthermore, because when we apply this to large problems, you don't have, you often cannot compute all the solutions and then do a subset selection. We want this method to be done online. So as you represent as you are computing the solutions. And then we also propose the integration of a decomposition method. So if you are looking at these large Pareto fronts, it is often not feasible to look at the whole Pareto front or to compute through the whole range of options. And so what we propose is that by assuming that our decision maker has previous knowledge on of the problem, we can decompose the Pareto front into sections of preferences of the decision maker between criteria, and focus our search in specific regions. So take, for instance, the top one example. You have here a Pareto front in the objective space, but just into objectives. So it's a bi-objective problem. And imagine that the decision maker, by having knowledge of the problem, knows that he prefers solutions that are that give a preference to objective 1 or to criteria 1 over criteria 2. Then what we say is that we can focus our search, we can divide the space and focus our search here on the left shaded, on the shaded part of the graph. On the bottom there is an example with 3 objectives. So here the decision maker would prefer solutions that favor objective 1 over 2 over 3. And this way we can we can limit our search region to more to regions of interest, more focused regions of interest. And then we also integrate this with an interactive method that through comparison of different solutions, eliminate inferior regions. So for instance, imagine we give the decision maker two solutions. Then if he prefers one solution to the other, we can eliminate from further consideration all regions that contain solutions that are inferior to the least preferred one. So how does our methodology integrates with the decision maker? So we start by defining with the decision maker by defining the problem and what would be our input data and our expected decisions, the objectives, constraints, and so on. So problem statement. Then, if the decision maker has previous knowledge of the problem and knows or has an idea of which criteria are more would in his view be more important, then we can, based on a partial order of criteria or on a total order of criteria, decompose and focus on the specific regions of the operator front, which we would then represent and generate a representation of the space. On the other hand, if the decision maker is not so knowledgeable of the problem and still wants to learn, then we would go directly to the representation of the problem. However, this is less efficient. And then, based on the initial representation, we would start interactive method and keep giving solutions to compare until a satisfactory solution is found. If from the initial subset of solutions there is no satisfactory solutions, we would represent again, and so on until we find a satisfactory solution or we reach the final end of the interactive method, of the learning stage of the interactive method. So just to give you an idea of this of the application, and this would be just some flavor on it. I'll show you a small, I'll show you, a case study on pharmaceutical supply chain design and planning, integrated design and planning. So we consider a supply chain with some suppliers, factories, and markets to sell these meningitis vaccines. And we have the raw materials that flow from suppliers to factories. Then the materials are used to produce a final product, and the final products are transported directly to the market. And then, for the transportations, for the logistics, we have road, air, and sea transportations, and these may be intermodal transportations. We consider 3 objective functions. So an economic objective function, and the availability, so the amount of final the availability is our social objective. So it's the amount of final product that is produced at a location where there is a higher incidence of disease, and the environmental impact of the supply chain. For our specific case study, so this is a bit generic, but for our specific case study, we took the production of meningitis vaccine, and the company currently has factories or has installed capacity for the production of this vaccine in France and in the US, and they consider adding a new factory in Africa, in South Africa. There is the advantage of having a higher incidence of disease, of meningitis, and then they would be producing closer to one of their major markets. So here is the application of our representation method to the supply chain design and planning. And here you can see on top left the percentage of total capacity allocated to the factory in the US, in the middle to the factory in France, and on the right to the factory in Africa. And this would be on the vertical axis, the environmental impact. Our social objective here on one of the horizontal axes, and the NPV, so the profit, on the other axis. And what we can see is that the factory in France has the highest and expected NPV, and when we want to have higher social benefits, so have a higher availability of product close to our market with higher incidence of disease, then we start shifting more production to South Africa, and lower environmental impact is found mostly on our factory in the US. This is basically because of the suppliers that we use. And also on the planning level, so on the transportations used, mostly as expected. So we have lower environmental impact. We use less the plane, and then there is some connections of the other means of transportation with the suppliers and the shape of the network itself. But we can see that if we locate a factory in France, as is here, with our higher NPV, then we mostly transport by boat, but we actually always transport a little bit by truck because there is intermodal transportation. So here, just to show you a little bit, and I'm almost finishing, just to show you a little bit the impacts of our methodology. When we apply to this case study, just a representation method, it takes more time to solve than when we add the decomposition and the representation as expected, because we are focusing on a smaller subset of the Pareto front.
Please.
Yes, almost finishing. And and we solve and we have less models solved. Then this is just an overview, but when we have the interaction, the complete framework, so the decomposition method plus the representation and the interactive procedure, we have much less iterations and number of comparisons required to the decision maker to reach our most preferred solutions, if we just represent and use the interactive method. So we propose an integrated methodology combining, just to sum up, three techniques that are usually studied separately. So representation method, definition of the region of interest, and an interactive method. And our results indicate that when we integrate these, we have a more efficient computation of the Pareto front, and integrating specifically the region of interest, or the decomposition method, brings significant gains to the computation of the Pareto front. Well, thank you very much for your attention, and I hope you find this interesting.
Thank you so much, Mariana. Now we start the discussion, Andrea, and you decide in which order you take the discussion. And I would say that we have, that we would like to finish at past, so you have 15 minutes,
Yes, so first of all, let me thank you, Dolores, you and the Euro Wisdom Forum for inviting me. It's a pleasure to be here. It's a pleasure to actually being aware of this, having the opportunity actually to talk to you guys and to also see this nice work. And this, of course, I would like to congratulate these young colleagues for the breadth and the quality of their work. This not only shows that how lively is the field, but also how much this work can have a practical impact and I would say also social impact, because the applications that have been presented today, going from disease spread to humanitarian operations to actually the last one on sustainability in supply chain by doing multi-objective optimization, they are also all very relevant from the perspective of the social good. So nevertheless, as a mathematician, what I like is also the part of the technical strength. The mathematical optimization component. Dolores presented me in this way, so this is the way in which I needed to push the attention. And so actually, again, congratulations. Seems to be all these methods seem to be very, very, very good for the topic. So I mean, advancing science in that direction. So I will follow just the order, and so taking my notes out, I would say, Kübra, I really like the application. I really like the Bender's decomposition perspective of the problem. I was wondering, just curious about if you thought about this as in terms of a bi-level optimization problem as well. So the way you can see some problems of this type is also adversarial component, and not in terms of the disease that generally doesn't have this, but in terms of your application, you're talking about misinformation and fake news and whatever. This is actually like an adversarial perspective, right? I mean, people are pushing into this direction. So did you guys think about this potential component of a bi-level optimization problem, so Stackelberg game and stuff, or this is maybe in the pipeline for the future?
Thank you for the question and for your comments, first of all. This is something that I addressed in my PhD study, actually. Two Stackelberg games, two problems in the form that you mentioned. Two players playing a zero-sum game. One wants to maximize the spread. The other one wants to minimize the spread. And there, of course, since in the bi-level context, the complexity, the computational complexity increases very much, we propose heuristic methods, heuristic methods, and they're smaller. We could deal with smaller networks, not like the ones we address in this one. But I find them quite relevant, actually, because considering both reactions of both players at the same time, I think it's meaningful. So this is not something that is in the pipeline, but something we had a look before.
Thanks.
Yeah.
Excellent. So going back, going in the order with Emilia, I again very much like the application. I can see it definitely for the humanitarian operation perspective, but the idea of try to merge different perspectives when you're collecting data, I think, is actually wider than that, right? I mean, it's like definitely something that we experience every day in multiple contexts. I was, if I catch the core components of your reasoning is you are actually using you're modeling and solving an optimization problem to define the consensus between essentially the different sources of information, right? I mean, that is the core part of your let's say proposal. Am I catching it correctly in that sense?
Yeah, absolutely correct.
Yes. So, and that part will probably depend very much on the type of consensus that you want to reach, right? I mean, it's like Again, it could be if you want to try to have an average, or you want to minimize, for example, the worst case, or doing a sort of min-max stuff. So is it really like, did you experience, tried to actually use different objectives in that context in order to define your major component there?
Yeah, many thanks for your question. What we've done is that this method is useful for every kind of optimization model using some kind of scenarios, right? So you can do that. And we played around a bit with this. What we in the pipeline are setting up now is using this methodology also for robust optimization, where you have ambiguity sets, and then to try to be not that as conservative and also reduce the level of ambiguity, and to try to be more robust to have these kind of ambiguity sets. So this is in the pipeline, but as you mentioned before, we did it, we played around, but this is a very general approach for using this in stochastic optimization.
Thank you, Emilia. Very, very, very interesting. So last, definitely, but not least, Mariana is very, I think multi-objective optimization is in some sense core in all the real world applications that we are seeing, especially with the spread. I mean, the availability of data, being able to actually collect way more data and being able to actually look at the problem from different perspectives. Very interesting proposal, the way in which you split the problem in the flowchart that you're showing us. I was wondering, the assumption, I see that the flowchart, you can avoid you can avoid the assumption of the decision maker having a knowledge of the problem. So being knowledgeable on what they want to achieve. But my question there is the type of knowledge that you are, at least in the way in which you presented it today, seems to be connected to a sort of constructing a hierarchy of the objective function, right? I mean, can you think
Yes.
about also knowledge of a different type, or this is really like more hierarchical objective function ordering for the decision maker?
Yes. Okay. So that's actually a very interesting question, because I think it's one of the parts of this work that could be much further studied. So my experience with multi-objective is that, okay, we have a lot of data, and I think it's a very interesting field, but for it to be applied in a real world, we definitely need to decompose the problems, because they are often very large. And so my idea was to try to have a decomposition approach that was very easy for the decision maker to convey their preferences. And so my idea was to have this sort of hierarchy that can be a total or just a partial hierarchy. So you can have more than two objectives in the same level of the hierarchy. And which would then become less efficient, because you need to explore a wider area, but it's still possible. However, yeah, so this was my assumption. So I wanted it to be easy, and that's why I chose this type of hierarchy. And I think that it's kind of applied to the real world, because even for instance, when we are searching for an apartment, searching for a hotel, you have your idea on what's your main pain points, or what's your main objectives, and so I think it's applicable. However,
yeah, I actually think it's true. I mean, I also think that is very natural to imagine in multi-objective optimization the fact of having a hierarchy of decisions of objective function. I was just curious to see if you can think about the decomposition also, not let's say, if you can imagine it vertically over the hierarchy of objective function, but more horizontally, so over other type of the characteristic of the problem.
Yes, I actually.
For example, the feasibility space, like, I mean, it's like thinking about what type of feasibility space I'm looking at or something like this. But I mean, again, it's a very open-ended question, so I don't,
Yeah.
I don't assume that you have a fully answer, but I found it interesting to imagine that this can be not only hierarchical in terms of the objective function, but more hierarchical versus some other characteristics that are not necessarily used in the objective function.
Yes, I have, so the methods I developed are very connected to the objective space. They are all working in the objective space. So that's why I had a bias to look mostly to decomposition methods in the objective space. But actually, when decomposition methods appeared, they were being applied in the solution space initially. But yes, I haven't explored that much in the solution space.
Anyway, for the three of you, excellent work. I hope we meet in person at some point and discuss more about these things. So this is, I mean, again, Dolores, thank you so much for the opportunity, and let's keep going doing this excellent work.
Yeah, thank you so much, Andrea, for the questions, and thank you, the three young women for the excellent presentations and the excellent answers. For the sake of time, I'm just going to show one more slide. So let me see if I can share quickly. Okay, it's me. So I'm going to show the audience one more slide. Yeah. So what I would like to tell you is a little bit what is happening from now onwards at WISDOM. So first of all, tomorrow we have a deadline for the next call of Young Women4OR. So the next round of 12 Young Women4OR. So hopefully we will announce this at the beginning of December, but you know, pretty sure it will be as in previous years. The second thing is that, as you know, we are the Euro Wisdom Forum, but we also have women in Alio. We also have WORM, we also have WORMs, and we are going to repeat the event from last year, or say the nature of the event from last year. So December 6, book the calendars. At 4 o'clock, say the Danish time, we will have a meeting of the 4 organizations. So I'm very looking forward to this. And as you know, we meet in person. So Andrea, that will be one of the opportunities. We meet in person at the Euro conferences. So we will have the usual Young Women4OR sessions and the satellite event and quite a few things. So for the ones who do not know enough wisdom, you know, you have a QR code there of our website, and we have a YouTube channel, we have a LinkedIn group. And I don't know whether Twitter is something that we should mention, or X, but anyway, we are still there. So yeah, that was all from me. So it would be great if we can now share our cameras and take a big picture, again, to advertise that to the wider public. So I will stop sharing my, oh, hello. Good to see you. Okay, so just in case. And as you know, we share those in the newsletters and also in social media. So thank you for showing. Okay, I have more people coming, so I do that. One more shot. Yeah, okay. So thank you very much to the young women for our speakers. And again, thank you for the audience. You also make this give a purpose for us to be here. So.
And thank you, Dolores, for moderating. That was really lovely. And Andre, thank you for the lovely insights. So looking forward to seeing everybody on the 6th of December. That's our next one.
Yes.
See you all then. Thank